Okay, in this video we're going to be looking at regression, and what we'll be looking at is how to find the regression line from a set of paired data, and also we'll be looking at some of the hypothesis testing that is related to regression. Okay, so let's start off with a definition of a regression line. Okay, the regression line is usually the straight line, and that straight line is the one that best fits the scatter plot of the data. Now, when we were talking about correlation, we did construct a scatter plot of data values, a pair of data values, and usually we can find a regression line that would be the best fit for that scatter plot of that data. So that's the definition of a regression line. Also, it's sometimes called a line of best fit or the least squares line. Okay. Okay, so here's a definition here. Okay, so they also call it the line of best fit or the least squares line. Okay, and in this case, we do have what they call the regression equation that describes the regression line. So here's the regression equation. And that's in this case y hat, and that's equal to b sub 0 plus b sub 1 times x. Okay. Now in this case here, this is similar to the equation of the straight line y is equal to mx plus b. If you recall from college algebra, you did talk about a equation of a line that's in slope-intercept form, and the slope-intercept form is y is equal to mx plus b. In this case here, your b sub 0, that's called the y-intercept, and that's the point where the regression line will be crossing the y-axis. And b sub 1, that's the number in front of x, that's the slope. The slope measures the steepness of that line. Okay, so in that case, right there, we do have an equation in slope-intercept form with a slope and a y-intercept. Okay. Now we can use that regression equation in slope-intercept form to come up with our regression equation. But before we do that, here you can see the y-intercept of the regression equation. For a population parameter, it will be beta sub 0, but for the sample statistic, is b sub 0. And the slope of the regression equation is beta sub 1, where for the sample statistic, it's b sub 1. Now for the equation of the regression line, if you're dealing with a population parameter, it's going to be y is equal to beta sub 0 plus beta sub 1 times x. For the sample statistic is y hat. That's equal to b sub 0 plus b sub 1 times x. Okay. Now, there are requirements when we get the regression equation, and that's this. The sample pair of data, that's your x and your y, is a simple random sample. Number 2, a visual examination of the scatter plot should show that the points approximate a straight line pattern. And then number 3, outliers can have a strong effect on the regression equation. So if you have any outliers that are known to be errors, you need to remove those, because outliers can make a difference in that regression equation. Okay. Now I'm just going to introduce the formulas for finding a slope and a y-intercept in the regression equation. Now for the b sub 1, that's going to be equal to r, which is a linear correlation coefficient, times the standard deviation of your y values over the standard deviation of your x values. Now, we will not use this in this video. Okay. Instead, it will be much easier to find the y-intercept from this. B sub 0 is equal to y bar minus b sub 1x bar. The y bar is your mean of your y values, and your x bar is the mean of your x values. If you recall, when you take the mean of a set of data, you take the sum of all your data values and divide by how many data values you have. Okay. Now, that slope is b sub 1, so instead of using this, we can use this formula, where n is the number of paired data, and that's multiplied by the sum of the product of x and y, minus the sum of your x times the sum of your y's. The denominator will be n times the square of all your x's, and you take the sum, minus the sum of all your x's, and then you square it. Okay? Now for the b sub 0, which is your y-intercept, we won't use that, because once we find this, we can find the y-intercept using this formula. Okay? Because you first have to find the slope in order to find the y-intercept. And then your round-off rule for your slope and your y-intercept, which is b1 and b sub 0, you're going to round those off to 3 significant digits at the end. Okay. Now, fortunately, our graphing calculator can do all of this for you, because you can get your slope and your y-intercept and use the equation to come up with your equation of the regression line. Okay, now we can use the regression equation for predictions. And here are 4 things you need to know. Use the regression equation for predictions only if the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well. And also use the regression equation for predictions only if the linear correlation coefficient indicates that there is a linear correlation between the 2 variables, as described in the last video. And then use the regression line for predictions only if the data do not go much beyond the scope of the available sample data. Because if we predict too far beyond the scope of the available sample data, that's called extrapolation, and it could result in bad predictions. And then if the regression equation does not appear to be useful for making predictions, then your best predicted value of the variable is its point estimate, which is its sample mean. And in fact, in one of the examples that I will do in this video, you will have a situation where that there's no linear correlation between the two, and then you'll have to use the sample mean as your best predicted value. Okay. All right. Here we have the pretty much the strategy for predicting values of y, and that's when you determine whether the regression equation is a good model. Okay, but in this case here, I do have this summary of finding the equation of the regression line, where you're going to be using this formula for b1, and then to find your b sub 0, you have to find out what y bar and x bar is. That's the mean of x and the mean of y, and then use those values and b1 to come up with b sub 0, and then substitute b sub 0 and b sub 1 into this standard form of the regression equation. And then to determine if a regression equation is a good model, you'll use that 8-step procedure for hypothesis testing, where you'll calculate R as the test statistic, and then determine if there's sufficient evidence of a linear correlation between the 2 variables. If there is, then you're going to substitute the given value of x into that regression equation, because the regression equation is a good model. If there is no sufficient evidence of a linear correlation, then you're going to be using y bar as the best predicted value of y hat. And that's the mean of the y values. Y bar is the mean of all your y values. Okay, so let's look at some examples of how to come up with a regression equation, and we're going to use our TI-83 or 84 plus calculator to do some of these problems. Let's start with this one. And also, I might as well mention that you're going to need this table. If you recall from the last video, that's the Pearson correlation coefficient table for your critical values. Okay, so we'll be using that to do some of these problems. Alright, this first example is this. Suppose IQ scores were obtained from randomly selected twins. For 20 such pairs of people, the linear correlation is 0.907. And the equation of the regression line is y hat is equal to 0.828 plus 0.93x, where x represents the IQ scores of the twins, both born second. Also, the 20x values have a mean of 96.13 and the 20y values have a mean of 97.45. What is the best predicted IQ of the twin born first, given that the twin born second has an IQ of 95? And then you're going to use a significance level of 0.05. So that tells me I have to do a hypothesis testing procedure for this, because I have the significance level given. Alright, so in this case, we'll start with step number 1, and that's stating the original claim. Now, usually the original claim is going to be this. We want to determine if there is a linear correlation between the two, so your rho is going to be not equal to 0. And then step number 2 is the opposite of the original claim. Well, the opposite of not equal to is equal to, so that means rho is equal to 0. And then step number 3, from that we can determine or write our null and alternative hypothesis. The null hypothesis always has the equal sign in it, so it'll be rho is equal to 0, and the alternative has the not equal to, so that's rho is not equal to 0. And I'm going to put the word claim there because your alternative hypothesis is your claim. And step number 4 is the significance level. That's alpha is equal to 0.05. That's given to us in the problem. So step number 4 is just your level of significance. Alpha is equal to 0.05. Now step number 5 is calculating the test statistic. Well, that's already given to us in the problem, because if you look at it, it says for 20 such pairs of people, the linear correlation coefficient is 0.907. So that's what R is equal to, 0.907. Okay, and now step number 6 is, now in this case we're going to have to use the critical value approach. Because the reason for that, we don't have any sample data to use. So, or raw data, I should say. So in this case here, my sample size is 20, so that's n, because I have 20 paired data, and the alpha level is 0.05. So to find the critical value, that's where we use that table of critical values of the Pearson correlation coefficient. So in this case, 0.05 is this column right here, and we go down to 20, which is here, 20, and a 0.05 level of significance will be 0.444. So the critical value there is going to be 0.444. Alright, step number 7 is our decision rule. Now, if you recall, when we were doing correlation, our decision rule is this. If the absolute value of R, since we're using the critical value approach, is greater than your critical value, you'll reject the null. And the absolute value of 0.907 will be 0.907. You're going to compare that to 0.444, which is your critical value, and you can see that 0.907 is greater than 0.444, which satisfies our decision rule. So that means we reject the null hypothesis. Okay. And then step number 8 is writing our conclusion. Well, here we just have to write a general conclusion here that there is sufficient evidence of a linear correlation. And you can take it a little further, saying that there's sufficient evidence to conclude that there is a linear correlation between the IQ scores of twins. Now, in this case, there is sufficient evidence of a linear correlation, so that means we can use the equation of the regression line as our equation. So I'm going to rewrite the equation y hat is equal to 8.28 plus 0.93x. Okay, that's our regression equation. And we're told to find the best predicted value of the twin born first, given that the twin born second has an IQ of 95. So in this case, x is equal to 95. So we just substitute the 95 in for x. So we have y hat is equal to 8.28 plus 0.93 times x. We're going to replace that with 95. And this you can type into the calculator. Just do 8.28 plus 0.93 times 95. You're going to get this value of 96.63. So in this case here, the best predicted IQ score of the twin born first, given that the twin born second had an IQ score of 95, will be 96.63. Okay. Okay, so that's pretty much how we will do that particular example here. Okay, now let's look at this next example. And here we're going to be using a graphing calculator for this. Here we're going to use the given information to find the equation of the regression line. And here we want to round the final values to 3 significant digits if necessary. Okay, in this case here, this is where we use our TI-83 or 84 plus graphing calculator. Okay, let me clear this screen. Okay, now the x values, that's this row here, that's going to go in L1. The y values will go in L2. So what I'm going to do here is press the stat key. Okay, the stat key gives me this menu here, and I'm going to edit. So I'm going to select number 1 for edit. Now notice I got data values in L1 and L2, so I want to remove those by, let's start with L1 using the left arrow key. Hit your up arrow key to highlight L1, then press clear and enter. And then for L2, use your up arrow key to highlight L2, hit clear and enter. That clears all those data values. Now in L1, I'm going to enter the x values. In this case, that's 24, 26, 28, 30, and 32. And make sure you hit enter after each data value. And then use your right arrow key to go over to L2 and enter those data values in the same order as your x values. So we start off with 15, 13, 20, 16, 24. And make sure you have the same number of values in L1 as you do in L2 because these are paired data values. Now I'm going to show you how to get the equation of the regression line from here. Okay, now you're going to press the stack button and then you're going to hit your right arrow key one time to highlight the calc menu. Now the menu item that you want is going to be number 4, and that's lin reg, which in parentheses says ax plus b. That's your linear regression equation. So you'll select number 4, or you can press the down arrow key to highlight number 4, and then press enter. And then go ahead and press enter again. Now in this case, it tells you the output where the linear regression equation is going to be of the form y is equal to ax plus b. Okay. Now what you're going to do here is substitute the value of a and the value of b in that equation. In this case, your a is 1.05. So this will be 1.05 times x, and then plus your b is negative 11.8, as you can see here, negative 11.8. Okay, now what I'm going to do here is write it like this, because the regression equation has y hat, and that's equal to b sub 0, that's your y-intercept. That's the negative 11.8 that goes first, plus b1 times x. That's your slope multiplied by x. That's this 1.05x. Okay, now that's the equation of the regression line. And that's all there is to it. So that's the equation of the regression line. Okay, here's another example of just that. Okay, in this case here, we're going to use the given data to find the equation of the regression line, and we're going to round the final value to 3 significant digits if necessary. Okay, so here's your table of x and y values. So in this case here, I'm going to press, I'll bring this up so y'all can see this, press the stack key, and then we're going to edit again, so select number 1 for edit. Now we're going to clear L1 and L2, so your left arrow key to go to the L1 column, use your up arrow key to highlight L1, and then hit clear and enter. We'll do the same for L2, go over to L2, use your up arrow key to highlight L2, press clear and enter. Now we can go ahead and enter the x values in L1, and the y values will go in L2. So your x values in L1 will be 1, 3, 5, 7, 9. Again, make sure you hit enter after each entry, and then use your right arrow key to enter the y values. So this is 143, 116, 100, 98, and 90. And I'm noticing something here. As your x values increases, your y value decreases. So I know we have a linear correlation. I mean a negative linear correlation. Because your x values are increasing. As they increase, your y values decrease. Okay? Now, to get that linear regression equation, press your stack key. And then hit your right arrow key to the calc menu and select number 4, which is your lin reg ax plus b, and then press enter. Okay, and that's going to be your A and your B, which you will use in y is equal to ax plus b. So let me move this over. And from that output, your A was negative 6.2. That's your slope. That's the number in front of x. So the y is equal to negative 6.2x plus your B, in this case, is 140.4. Okay. Now, if we're going to write it in the form for our linear regression equation with y hat, the y-intercept goes in front. So this will be 140.4, and then this negative 6.2x goes last. So it'll be minus 6.2x. Okay, so that's the equation of the regression line from this set of data. Okay. All right, now the next example, we're going to be dealing with, let's say we had this data, and we're also going to use our graphing calculator as well. The data shows the time intervals after an eruption to the next eruption of a certain geyser. Find the regression equation, letting the first variable be the independent variable, or your x value. Find the best predicted time of the interval after an eruption, given that the current eruption has a height of 113 feet. You're going to use the significance level of 0.05. Okay, so here we're going to do like we did on those last two examples. First of all, we're going to find the equation of the regression line. Or we can say regression equation using the calculator. Okay. And I'm going to have to put this calculator in front of this, front of those numbers here. So let's see, clear. Go ahead and press the stat key. The stat key gives you this menu, so you select number 1 to edit, and to clear this, go to L1, highlight L1 using the up arrow key, press clear and enter, and then L2, do the same thing, clear and enter. Okay, now your L1 is going to be your x values, which is the height. Okay, so in those individuals, so it's 96, then 128, 75, 128, 88, 73, 80, 96. Make sure you hit enter after the last number. Then hit your right arrow key to go to L2. And then you're going to enter the interval after. That's 66, 85, 59, 86, 70, 75, 73, 75. And enter. Because you want to make sure that you have the same number of data values in L1 as you do in L2. Okay? Because these are paired data values. Now let's go ahead and get that regression equation by pressing the stat key. And then hit your right arrow key one time for the calc menu. And then you're going to go down to number 4, which is your linear regression, ax plus b. And then hit enter. And then hit enter again. Okay, so here the linear regression equation will come from the a and the b, and we're going to round a and b to 3 decimal places in this case. So we know that's y is equal to ax plus b based on the that comes from the calculator, because linear regression equation is ax plus b, that's given to you. Your a is 0.322. So this will be 0.322x plus b is 42.865, rounded to 3 decimal places. 42.865. Okay, that's your regression equation. Okay, now here, watch. written this way would be 42.865. We write the y-intercept first and then plus the slope with the x behind it, 0.322x. So y hat is equal to 42.865 plus 0.322x. Okay, so that's your regression equation. Okay, now we're told to use a significance level of 0.05 because we want to find the best predicted time of the interval after an eruption, given that the current eruption has a height of 113 feet. So we need to do the hypothesis testing procedure. Okay, so in this case here, step number 1 is the original claim. Now in this case here, we say rho is not equal to 0. That means that there is a linear correlation between the two variables, height and interval after. Okay, so rho is not equal to 0. Step number 2 is the opposite of the original claim, where rho is equal to 0. And then step number 3 is the null and the alternative hypothesis. The null has the equal sign in it, so it'll be rho is equal to 0, and your alternative has the not equal sign, not equal to symbol in it, so it'll be rho is not equal to 0. And then step number 4 is your level of significance. In this case, it was 0.05, so your alpha is going to be 0.05. That's your level of significance that's given to you in the problem. Now, step number 5 is calculating the test statistic. And here we're going to be using R as the test statistic. Let me show you something on the calculator here. When you did the linear regression for y is equal to ax plus b, and the reason why I had you to select that lin reg ax plus b, notice you have your correlation coefficient given to you. That's this last number right here. That's your linear correlation coefficient, which is your R. That's your test statistic, which is in this case 0.778. And that's rounded to 3 decimal places. So in this case here, 0.778, that's your test statistic. Okay. So in this case, you didn't have to use that formula for R to find out what that test statistic is. Because in this case, when you did the linear regression for ax plus b, not only did it give you A and B, it also gave you the R, which is your linear correlation coefficient. Okay, now step number 6, it'll be best to do the critical value approach because we know what R is. Okay, because the only thing we need is this. N is the number of paired sample data. In this case, we got 1, 2, 3, 4, 5, 6, 7, 8 paired data values. So in this case here, N is 8. And the alpha level is 0.05. Those are the only two we need to get our critical value. And this is where we use that table for your critical values of the Pearson correlation coefficient R. So here we have 8 data values, and we're at the 0.05 level. That means that your critical value is going to be 0.707. So 0.707 represents your critical value. And then step number 7 is your decision rule. Since we're using the critical value method, our decision rule will have to be this. If the absolute value of R is greater than your critical value, you're going to reject the null hypothesis. Now in this case here, your R, which is your test statistic, that's 0.778. Compare that to the critical value of 0.707. You'll see that 0.778 is greater than 0.707, so that satisfies our critical value, our decision rule. So we say we reject the null hypothesis. So here we're rejecting the null hypothesis. And step number 8 is our conclusion. So we say here that there is sufficient evidence that there is a linear correlation between the height of the eruption and the time interval after. Okay, so here we say there's sufficient evidence that there is a linear correlation between the height of the eruption of a geyser and the time interval after that eruption. Okay, since there is sufficient evidence of a linear correlation, we can use this regression equation of y is equal to 42.865 plus 0.322x to find out what would be the interval after an eruption given that the current eruption has a height of 113 feet. Okay, so here's my equation. Y hat is equal to 42.865 plus 0.322x. And in this case, my x was going to be 113. So the height in question that we're dealing with is 113 feet. So we just substitute 113 for x into this equation. So we have 42.86, that should be 865, I'm sorry. $42.865 plus 0.322 times x, and x is going to be 113. So in this case here, if you do 42.865 plus 0.322 times 113, you should get, for y hat, 79.3, and this is going to be in minutes. So in this case here, the best predicted time of the interval after an eruption, given that the current eruption has a height of 113 feet, is 79.3 minutes. Okay, I'm going to do one more example, and this will be the last one I'll do in this video. Alright, in this case, the data shows systolic and diastolic blood pressure of certain people. Find the regression equation letting the systolic reading be the independent variable or the x variable. Find the best predicted diastolic pressure for a person with a systolic reading of 148. Is the predicted value close to 90.2, which is the actual diastolic reading? Use a significance level of 0.05. Okay, so here again we can use our graphing calculator to enter those data values here. Okay, so in this case here, we press our stat button, and then we're going to edit because we're entering new data. So you select number 1 for edit. Now let's go ahead and clear this out. Left arrow, and then highlight L1 using your up arrow key. press clear and then enter. And then for L2, do the same thing. Highlight L2 using your up arrow key, then clear and enter. Alright, now in this case here, we'll enter the systolic readings. That's your X values. They will go in L1. So those are 139, 112, 113, 150, 129, 112, 128, 139. Hit your right arrow key to go to L2. Enter the diastolic readings. Oops. Your diastolic readings here are 102, 83, 57, 87, 72, 80, 67, and 74. Okay. We want to make sure that the number of data values in L1 are the same as the number of data values in L2, because these are paired data again. Alright, now for the regression equation. Press your Stat key. Use your right arrow key to go to the Calc menu. Select number 4. And then press Enter. Okay, so in this case here, let me move this off to the side and just say here regression equation. Which is, according to our TI-83 or 84 plus calculator, is always y is equal to ax plus b. So in this case, you're looking at this, your a to 3 decimal places will be 0.420. Okay, so we got y is equal to 0.420 x plus b, and b is this number right here to 3 decimal places, 24.110. Okay. Now, the way we write the regression equation, we use y hat, and then we put the y-intercept first, so 24.110 plus 0.420 x. Okay, that's going to be your regression equation. Okay. Now we're going to be using that regression equation a little bit later, because we have to do a hypothesis testing, because it says use a significance level of 0.05. So in this case here, step number 1 is the original claim. Now usually we want to test whether there is a linear correlation between the two variables. So here we say rho is not equal to 0. That there is a linear correlation between systolic and diastolic readings. Step number 2, the opposite, means that there is no correlation between the two readings. So rho is equal to 0. And then step number 3 is your null and alternative hypothesis from steps 1 and 2. The null has the equal sign, the alternative has the not equal to. And in this case, this is going to be your claim of whether there is a linear correlation between those two variables. And then step number 4, your alpha level, in this case that's 0.05. That's already given to you in the problem. Alright, and now step number 5 is your test statistic, which is your linear correlation coefficient. Now I'm going to go ahead and bring the calculator back up here. When we did that linear regression for y is equal to ax plus b, we also got the linear correlation coefficient, which is right here. That's going to be 0.446 rounded to 3 decimal places. So your linear correlation coefficient in this case would be 0.446. And then step number 6, we're going to use the critical value method because we know what R is. Okay, so here N is the number of paired sample data. Here we got 8 paired data values. So N in this case will be 8. And the alpha level was 0.05 that was given to us. So here, to find the critical value, that's where we use that table of critical values of the Pearson correlation coefficient. Here, 8 data values, and the alpha level was 0.05, so that means that 0.707 is the critical value. Okay. Alright, now step number 7 is our decision rule. Since we're dealing with the critical value approach, we have to use this decision rule. If the absolute value of R is greater than your critical value, you're going to reject the null. Okay, if the absolute value of R is greater than your critical value, you reject the null. Here, the absolute value of 0.446 is 0.446. And then we compare that to the critical value of 0.707. In this case, 0.446 is less than 0.707. This does not satisfy our decision rule, so that means we fail to reject the null hypothesis. We fail to reject the null hypothesis. So when we fail to reject the null hypothesis, that means that there is no sufficient evidence that there is a linear correlation between systolic and diastolic blood pressure readings. Okay. There is no sufficient evidence there is a linear correlation between systolic and diastolic blood pressure readings. Now, when there is no sufficient evidence of that linear correlation, then what that means is this. We have to use y bar as our best predicted value. Okay? So if you recall, I'm going to bring this back up here. If there's no sufficient evidence of a linear correlation, then the best predicted value of y hat is going to be the value of y bar, which is the mean of your y values. Okay, so in this case, we need to find out what y bar is. Now let's go back to this table here. The systolic values are your x. Your diastolic value is going to be your y. Okay? So now, to find out what y bar is, that's the sample mean of all your y values. We take the sum of all your y's and divide that by n. And in this case, there are 8 data values here. So let's go back up here and add up those data values here. So if I have 102 plus 83 plus 57 plus 87 plus 72 plus 80 plus 67 plus 74, and I'm going to go ahead and put this up here so you'll see that I'm just adding those data values here, adding up just those y values. That's going to give me 622. And then take 622, divide that by 8. So 622 divided by 8 would give me a mean of 77, rounded to one decimal place, 77.8. So the mean of all your y values is 77.8. So in this case here, since there's no sufficient evidence of a linear correlation, your best predicted diastolic pressure for a person with a systolic reading of 148 would have to be the mean of your y values, which is in this case 77.8. Okay? Now, to answer the question, is the predicted value of close to 90.2, which was the actual diastolic reading? The answer there is no. It's not close to that actual diastolic reading. It's a little bit, it's way off. Okay? So this is how we can use our graphing calculator to even come up with regression equations and also determine the best predicted value by doing a hypothesis testing procedure. So that will conclude this video on regression.